When Joe Neanderthal, the caveman, battled it out with his enemy, it could be the only advantage held by either man was that one had a thicker skull. If so, the near equalization of weapons did not last long. Even primitive man, with his instinct for self-preservation, soon developed a better weapon, one he could use at longer range. When man built a fortress to defend himself, another developed a catapult that hurled ammunition. Thus, the struggle to develop weapons and counterweapons continued through the centuries. The invention of the airplane added a new dimension to warfare. And for a time, the bomber aircraft went unchallenged except for an occasional interruption. Early World War II marked the beginning of a new era, which saw electronics employed in warfare. Radar, developed by the Germans, British, and Americans, provided early warning of approaching hostile aircraft. This was to be followed by radar jamming by mechanical and electronic methods. To see how mechanical jamming works against radar, we have only to remember the basic principles by which radar functions. Basically, radar depends on the reflection of radiated energy. If enough energy is reflected from an object, it will be picked up by the radar antenna and appear as a blip or radar echo on the radar scope display. The size and brightness of the blip on the radar scope will depend, among other things, on the amount of energy returned to the radar. The only way a radar echo can be identified as an aircraft is by its relative size, shape, velocity, and height. Mechanical jamming is accomplished by introducing various devices into the radar beam, which are capable of producing echoes like an aircraft. A relatively small number of highly reflective metallic foil devices, for example, can produce many false target echoes. To the untrained operator, the appearance of many such echoes can be confusing. Aluminum foil chaff falls at the rate of approximately 200 to 300 feet per minute, depending on the altitude and the speed of the winds aloft. Thus, a drop from an altitude of 20,000 feet may remain on radar scopes for an hour or more. Because of the turbulence of the slipstream of the aircraft, an airborne chaff drop spreads quickly to about a half mile, after which it blossoms and drifts with the wind at the same speed as the winds aloft. In World War II, both the Germans and Allies had a mechanical jamming capability. The devices in the electronic warfare inventory of both sides included chaff, foil strips cut into various lengths and used primarily against high-frequency radars. Rope, strips of foil several hundred feet long and employed against low-frequency radars. And the corner reflector, a multi-sided device designed to produce a radar echo at all frequencies. The Germans withheld using mechanical jamming, hoping to avoid reprisals against their radars. The decision of the Allied command to use mechanical jamming was predicated on the need to conduct large-scale bombing raids against German industrial targets. To avoid untenable losses, the bombers required protection against radar-controlled anti-aircraft artillery and radar-equipped fighter aircraft. In the Allied raid on Hamburg in June 1943, more than 30 tons of aluminum foil were dropped by Allied aircraft. The result was a 75% reduction in bomber losses, compared to those suffered previously in similar strikes. The use of mechanical jamming by the Allies continued throughout the war. Initially, chaff units were dropped from each aircraft in the formation at predetermined rates. These early drops were made by hand, with crew members tossing units out of open waste windows. Later, the development of automatic dispensers led to the use of chaff dispensing ships. These aircraft preceded the formation of bombers and dispensed chaff at saturation rates along the bomb run.